So welcome everyone to I believe, fifth talk of the fourth talk of the Equivariant Elliptic Cohomology Seminar. So today we have Marco Giustetto from University of Osnabrück, and Marco will be telling us about Orbispaces. So Marco, please take it away.
Sure. Thanks for the introduction. So the goal of today is to introduce this theory of Orbispaces, which is a tool to define equivariant homotopy and equivariant cohomology theories without needing to specifying a base group, which we take. However, before we enter into this story, let me tell you a bit about the classical story of equivariant homotopy theory. The players in here are what are called G spaces. I may indicate with G top the category of topological spaces equipped with the action of group G, where maps are.
Can you?
Yes.
Yeah, there seems to be a problem. Like everything's
the
super
quality
blurry.
of the video went down.
Yeah. Yeah, it
quality
kind of. Yeah, it's not readable anymore.
And let me.
I'll pause the recording. I'll stop the recording if you want. So yeah, after getting everything all fixed, let's continue the talk. So please, Marco, please take it away.
So as I was saying, in equivariant homotopy theory, we care about just G topological spaces, and we basically redefine all classical tools of homotopy theory in here. How? But the point is that if you have a morphism of groups, let's say from G to H, then you have some induced maps between the categories of G spaces and H spaces. The classical one is simply that if you have an H space, you can view it as a G space by composing the H action with F. Therefore, you can change coefficients. And if we are, although we can do it completely in general for any group, let me consider the special case where we have here the point, the trivial group. So, spaces with an action on the trivial group are simply spaces themselves. And we have two interesting adjoints now of this functor. One takes G space here and picks the quotient of the space with respect to the action, while the other one picks the subspace of points that are fixed by the action. And if you view these as infinity categories in particular, we need to define this appropriately so that this becomes the homotopy quotient of the action, and this becomes the homotopy fixed points, with the appropriate care that the two things are quite different, with homotopy and without. And having this, we can again redefine a bunch of things. So the first thing is how do we define a geomorphopy equivalence? This is the classical definition, but where now the interval comes with a G action, which is the trivial one. how do we define G spheres? Well, here we have two very sensible choices. First one is that for any closed subgroup H in G, I didn't say it, but whenever I'm saying groups, I mean topological groups. What I can do is that I can consider the quotient is canonically a G space by the action induced on G itself by G itself. I can point it. There's still this quotient is still a topological space, so this makes sense. And then I can smash with an N sphere, where here I've taken some base point. And this is actually the choice of spheres, the family of spheres that we will concern ourselves with for today. But let me mention that there is another choice, which is if you have an orthogonal representation of G, that is, if you have a map from G to the orthogonal group, denote it, ORN. Orthogonal isometries of Rn. We call this representation here V. Well, what I can do is that I can take the one-point compactification of Rn, then the action of the representation of G induces a G action on this compactification, which is going to be Sn. So we get this representation sphere. But the G action indeed is induced by this representation. I'm not going to need this for today. We can talk about GCW complexes. Maybe denote these families as 1 and 2. This is built as the classical definition from spheres of this type. We can talk about equivariant homotopy groups. The unstable ones. And let me give you a spoiler. Since we defined GCW complexes in this way, and for classical CW complexes, we have a Whitehead theorem. We want ready to put the definition of equivariant homotopy groups that gets you that gets us there more or less. Hence, we care about these kinds of spheres. Therefore, we will have for any a closed subgroup H of G.
Sorry, may I have a very elementary question?
Yes.
When we build CW complexes, like non-equivariant CW complexes, then we use disks and we glue the boundaries of the disks, right? So we
Yes.
need to say somehow what the action on the whole disk is. No.
Yes, but here you're taking the trivial G action on the sphere. You have a G action here.
Yeah.
On this quotient. This gives an action on the whole thing.
Okay.
Should I say a couple of words more?
Maybe. Yes.
So actually, this is for the. That is the pointed variant. If you want an unpointed, you can consider the following pair. You take the H times Sn minus 1. What H times D n minus 1, which is simply the n minus 1 sphere into is the n minus 1 disk. Maybe the n disk, pardon. And the point is that if you view this as a G space with trivial G action, both the second factors, and you view this quotient as a G space via a multiplication on G, then these become G spaces themselves, where the action is simply defined by the action component wise. The inclusion of the boundary of Sn minus 1 into Dn extends to an inclusion of these G spaces, and the inclusion itself is G equivariant because it is separately on both factors. And this gives you the disk boundary pair that you wanted.
Okay, makes sense. Yeah, thanks.
Welcome. Okay, so back to our homotopy groups. So again, we have G space. We have a closed group of G, which is this H here. We have an index. How you classically define so ignore for a second the closed group. How you would define the nth homotopy group of n, be taking the n sphere and n after choice of base points for both. And here, what we do is that we take this sphere here instead, this G sphere. Take G mod H pointed, which is n. And of course, we care only about G equivariant maps. And the square brackets means that we are taking G homotopy classes of maps, where since we have defined G homotopy equivalence before. And it turns out that this thing is actually something that we can compute already ordinarily, because this is simply the adjunction. This is the ordinary non-equivariant nth homotopy group of the H fixed points in M. Which is defined again by using M as an H space, because you can bootstrap the G action to just an H action and then taking fixed points. And now that we have all of our players, we can state two results that show that this theory is interesting. First is, as mentioned before, that we have an equivariant Whitehead theorem. That a map between GCW complexes is a G homotopy equivalence if it induces isos on all homotopy groups. All of this under a technical assumption, however. It is that G is to be a compact Lie group. This still comprises a bunch of interesting cases. In particular, if G is finite, this is not a problem. A bunch of subgroups of GLN, also compact Lie groups. Also, mention another thing to make this technical assumption less scary. That is that, maybe I should clean the board and the white, and that is that the category of compact Lie groups and homomorphism of them is actually a full subcategory of the category of topological groups, which is a priori not entirely clear why, because compact Lie group is a group object in manifolds, meaning that all the defining maps need to be smooth. In particular, morphism of Lie groups needs to be also a diffeomorphism of manifolds. But magic, if morphism between compact Lie groups is a continuous morphism of topological groups, it is automatically smooth. So being compact Lie is really just a property of a topological group. Okay, so it is nice. This tells us that we have some sensible theory. But what is even nicer is that we have another theorem. By Elmendorf. So as we said, if G is a topological group and H is a closed subgroup, the quotient G mod H is a G space. And therefore, let us consider this category here, called the orbit category of G. There's a category whose objects are exactly all those quotients. For H closed subgroup. viewed as a fully faithful subcategory of Orbispaces. And now the statement is that there is an equivalence of infinity categories, or the original language of the homotopy categories, but we have grown ups now. Between the category of G spaces and the category of presheaves valued in spaces, in anima, on this category that we defined here. And how is this realized? We have G space M. We send it to the functor that takes an object here, so H, and sends it to the H fixed points of M. So this result builds up on the equivariant Whitehead theorem. Also, although this has been generalized, the original proof requires as well that G is a compact Lie group. And essentially it tells us that the equivariant homotopy type of M is really contained in the classical, represented by the classical homotopy type of its subspaces of fixed points, ranging over all closed subgroups of G. And so this is the classical picture. Now the point is, do we need to specify G at all? Because when you consider a G space, what a G space really is a G module. So if you think about the classical definition of module over a ring, well, the definition of G space is exactly the same thing, just rephrasing. And the point is that for modules, we don't need to talk about modules over a ring necessarily. We can talk about a general category of all modules, where objects are couples of a ring and a module over that ring, and morphisms are morphism rings and morphism modules which respects the induced structures. And so the dream is, can we do something like this also in this context? And in particular, since we have defined what G equivalence, so an equivalence in this category here is. So we know what does it mean to build an equivariant functor out of here. Particularly, we want to build a G equivariant cohomology theory. It's going to be a homotopy invariant functor from this category to abelian groups, for example. How can we do this, however, without having to specify G all the time? With the advantage, for example, that we can do certain computations for one group and then carry them over to other groups via base change. And this is the starting question for the theory of Orbispaces. Now, before we get there, however, let me say a couple of words more about his idea of G spaces as modules, because it's going to come in handy in a second. Namely, I want to talk now about topological groupoids and stacks, which allow us to make that comparison before a bit more precise. It's still readable. Yes. So let me define this category here of topological groupoids. Now, this is a subcategory of Siegel objects in spaces. Such that all objects in X1 in the space of maps here are invertible. Usually topological groupoids are stated by truncating this delta up to just a delta smaller or equal than 3. But that's not that's no difference.
Sorry, it's hard to read the smaller font. So, and on the left it says fun, and what is
Yes.
on the
So these are
superscript?
Sure. So these are Siegel objects in spaces.
Mm-hmm.
So some things which are such that the map from xn to x1 times x1. Here I have it. And times are equivalences for n greater or equal than 2.
And on the right it says x1 or x.
Yes, it is. So the point is that we use them. Let me say it to the idea behind it before the definition. We look at the degeneracy. Sorry, the phase maps in delta as encoding some sort of multiplication, and the degeneracy maps as encoding how to specify identity elements. And this way we can talk about the objects in X1, which are this X1 invertible, which are sorry, let me say this before. So under this perspective, X0 is the space of points or space of objects of your topological groupoids. X1 is the space of maps of your topological groupoids. X2 is the space of composable arrows in your topological groupoids, and so on. And the objects in here are the objects such that maybe let me write it like this. So it's true is this form. We have in particular the map D1, the face map that goes in X1. In X0 we have the degeneracy map S0. Now the point is that D1 defines the composition, my topological groupoid. S0 defines for each object a unit morphism from the object to itself. And X1 inverse, those maps here, which admit a second map such as pre and post composition is the identity. Or yes. Does this make some sense, or should I write it down more explicitly?
I just wanted to know what the superscript is over Xn in that.
Okay, so I wasted breath. Yes, the space of a subspace of X1 composed of arrows that admit a left and right inverse.
Okay, very good, thanks.
So what are concrete examples of this? Classical groupoids. Where X0 becomes simply the by classical I mean really one groupoid, so X0 becomes the set of objects, X1 becomes the set of morphisms, and so on. In particular, we can also do it for groups, but notice that if we have topological groups, G, we can associate to it the topological groupoid, which has the point, space of objects, G, space of morphisms, which maps here above the trivial one. And you encode the multiplication of G as this face map here, whereas the other two face map are simply the projections. Say on the second factor and on the first factor. Also here you have degeneracy map, the map from the point to G, so the point in G, which corresponds to, I change color, corresponds to the identity. Another trivial example you can do is that if you have a topological space, you can associate to it also a topological groupoid in 2 ways. Which are both trivial but friendly. First, you can consider the topological groupoid. Also, by the way, this thing here goes forward, but it's clear how. So again, topological space, we can consider the topological groupoid where I always have identity maps, also on x0. Or I can define the pair groupoid where I have point, then x, x times x, did something wrong? Yes, forgot one multiplication. All the maps are given by projections. And also, if you have a group acting on a space, so G space, you can also encode this into a topological groupoid. So notice that I'm awfully late, so I'll try to speed up a bit. So if you have a space M in particular, it means that you have a map from G times M to M. And you have the following topological groupoid that you can write. If you're G times M and you want to go to M, one way you can do it is via the projection, the second factor. Or you can take this action. And what we expect of an action of a group on a space is that it is compatible with the group structure. And here I can go G times N. Here I put projection to the second part. Here I put the multiplication on G. And here I put the action again. Not that, and here I continue the same guys. And now that this is enough to encode that the action is compatible with the group structure. Also, this does define a single object, because you can identify this with fiber quotient, these two maps. And it is you also have that all the paths, so the objects in here, weight and inverse. Now, why are topological groupoids useful? Because in particular, you can associate to them their realization. They are functors from delta opto spaces. You can take the co-limit. Fine. This guy is. In particular, the classifying space of a group is essentially by one of its definitions. The geometric realization associated to the topological groupoid that I wrote before. If you have an action of a space, if you have a G space, can define the quotient of M by this action. Exactly as realization this topological groupoid here. Usually sort of like this. Now, I think I'm a bit late to introduce stacks, so let me actually skip them altogether because we don't need them for the statements that I'm going to write. And let me define the orbit category. Also, let me give a couple of names that I forgot. In particular, if I have my topological, if I have a topological group, I call this topological groupoid BG, called B. Also here this becomes the topological realization of BG. Now we define the orbit category, orb, as a full subcategory of the topological groupoids spanned by this classifying topological groupoids, you wish. Particularly, we restrict with the intent of using Elmendorf's theorem later to compact Lie groups. Take this as a subcategory of topological groupoids. Let me mention one thing that didn't really talk about, and that is when I defined this category of topological groupoids, I didn't specify its mapping spaces. And the point is that you can, there are two choices that you can make. One is the canonical one. It's a functorial category, so you can just take natural transformations. But there is a trick. First, that's the general fact that if you have a Cartesian closed category, and let's assume it's also co-complete. Then any functorial category that has a codomain E has the same properties. Also, if we take our category of topological groupoids, for sure it's going to be since it is Cartesian closed, it's going to be enriched at the very least over simplicial spaces. One then checks that it is internal mapping spaces that one has for free do satisfy the Segel condition, and also this invertibility of paths, meaning that the category of topological groupoids is enriched over itself. So given two topological groupoids, you can form a topological groupoid of maps between them. And let me go here. The actual definition of mapping spaces that we put on top GPD going to X and Y. Is by definition the geometric realization of this internal home. Which is, as I said, geometric realization of a topological groupoid. This makes sense and behaves well with respect to composition because geometric realization is gentle at the very least with products. So when we define, when we define this category orb, these are the mapping spaces that you want to have in mind. And now the question: are these things actually computable? Can we make sense of this? And the answer is yes. Which is one of the main things that I wanted to get at. The position is the following: that they are computable, and if we have two elements in here, correspond to Lie groups G and H. Well, it is nothing more than the space of maps of topological groups from G to H with an identification, where we quotient by the conjugation action of the codomain. this H acts on itself by conjugation. Particularly if you have a morphism from G to H and an element in H, you can just conjugate pointwise. This defines this action of H on this mapping space. How do we see this? Well, first of all, let me mention two points of view that one can have on this result before showing it. The first one is that classical exercise in like category theory is that if you have two groups and if you view them as groupoids canonically as groupoids with 1 point and loops on that point representing the objects of your group, then a functor from a groupoid like this, say G, to another group that is H, is exactly of this form. So it's just a morphism G to H, and the natural transformation between two such functors is given by a conjugation by an element of H. So since here we are talking about talking infinity categories, so we don't see homotopes. It makes sense that we have this quotient here. Another point of view on this is that I should remind you of the fact that the difference between the mapping space between two unpointed spaces and between two pointed spaces. The way that if you forget base points, what you have is an action again by conjugation of loops of the target space on the mapping space. And we are going to make precise also the second point of view in a second. So with that said, let me do the proof. So it's basically unraveling definitions, but we need a thing. We need to know the topological groupoids of maps from BG to BH. And we have that this is indeed a topological groupoid, or is the topological isomorphic to the topological groupoid associated to the conjugation action of H on maps from G to H. So we have, as we were before, we have maps from, maps of topological groups from G to H. We have H times same thing. Projection conjugation. And one does it component-wise, because we have a formula for this, namely you have that if you have two groupoids, topological groupoids X and Y, and we want to compute what this internal mapping object looks like at stage n, by the fact that so by Yoneda, essentially, you can write this as space of maps. So I'm using this really to mean the maps in the classical senses, natural transformations between x times delta n and y, where it is delta n is we view it as a topological groupoid by the inclusion sets into spaces as usual. However, what this means concretely, if we write this down, so we see that at level 0, this thing here is just the space of maps. Those are the morphisms of the topological groupoids. BG and BH. The 0 is trivial degrees, and again by the same way as you show it classically, it is simply given by maps of groups from G to H. What about degree 1? It gets a little bit tricky. Not conceptually, of course, but just with computations. Because the problem is that this delta 1 is not constant in all degrees, of course. So when we write it down concretely, it looks like the following. Maybe already see the computation you added, that is with 0. Delta 1 of 0 will have we are set with 2 objects, 0 and 1. Degree 1, it will have all the elements 0, 0, 0, 1, 1, 1. So the one simplices inside delta 1. In degree 2, it will have 4 objects, and so on. So the natural, this object here looked like it's the same color. 0, 1, you have then G times 0, 0, 0, 1, 1. Then you have G times G times a set with 4 elements. So let me just write it like this. We want another transformation to this other functor here. Here there's nothing we can really something we can really do. There's only one map. If we consider the maps here that can fit in, well, playing around with the simplicial identities, you see that they are the form F1 alpha F2, where F1 and F2 are really group morphisms from G to H. Alpha instead not, because for example, you cannot, alpha corresponds to a map from G times 0, 1 to H. And since it doesn't lie in the image of this generacy map, for example, alpha is not even required to preserve the identity element. And let me take the direction. And then if you go forward, you see that the element here is of the form F1 times F1, F1 times alpha, alpha times F2, F2 times F2, then you play around with, again, with the simplicial identities, and turns out that you have the following relation. F1 of G times alpha of some other G prime must be equivalent to alpha of G times G prime. We compose with the morphism giving you the identity in place of G prime. F1 of G times alpha of 1 G, the same as alpha of G. You have the same for F2. And so now you see what is alpha is. Alpha is the composition of F1, and alpha of G is F1 of G multiplied by some constant in H. The same for F2, but in the other way around. We have and therefore you see that you have that one of the two morphism is conjugation of another one, the other one. This eta is alpha 1. And plug this into the bracket. So in particular, this datum here is really equivalent to the datum of a single element in H, this eta here, and one of the two morphisms. Then you turn the other one of conjugation. You can continue to the trick for all n, and therefore you see that it is a topological groupoid is of this form that I wrote here. And now we're done, because by definition, this is a full subcategory. So the maps in here, the mapping space in here is really the mapping space at the level of topological groupoids, and which is the geometric realization of this guy. And the geometric realization of a topological groupoid associated to a G space, about here is to an H space, is the homotopy quotient. And hence you get it. And I think I can. No. It is here. So let me substantiate now the claim that I made before. This is related to actually to base points, because in particular this shows you that I mean you have a functor from groups, or in our case compact Lie groups, to topological groupoids. And in particular, it is a system from groups to orb. And by the formula that we wrote before, this definitely cannot be fully faithful, because the mapping space in the target category is a quotient of that in the starting category, and a non-trivial quotient. However, you can notice one thing. That when we take our functor from compactly groups to the orbit category, but a compactly groups is really compactly groups over the trivial group, right? Because this is a point in particular terminal object. Therefore, this functor here will factor through orb where we take pointed objects, because objects here again are really, maybe taking the slice is not going to help, but the pointed objects, so they're going to have a preferred choice of point here. And the choice of point is that if I take group G, associated to the map coming from the unit. And the point is that the functor from this functor from compactly groups to pointed objects in orb is fully faithful. Because if you consider now my bad, not just fully faithful, but it's really an equivalence. Because the fact that it is essentially surjective is by design, because we constructed orb to have objects of this form. And if we take a pointer object in here, in particular, all choices of points are going to be homotopy equivalent. So up to equivalence, we reach every object in here. But this is no mystery. The point is that the functor now is fully faithful. Why? Because if we have any two groups H and G, you can look at the following square. Take maps logical groups from H to G, modulo the so take the quotient of the action of the conjugation action of G on this, and again we have a stupid morphism from the point to H. It's simply picking the unit. So we have an induced morphism here. And now if we put the point here, take this quotient. This is just not so clever disguise for the classifying space of G. Because the point with a trivial G action, sorry, if you take topological groupoid associated to a point with trivial G action, you get simply a topological groupoid associated to the group itself. And in particular, if you take considering the conjugation action of G, and so you get as a realization Pg. And we can consider the same thing about orb. So without fixing base points. We have induced map here. We have the same induced map here by picking the unit. Point to sorry, doesn't make a difference, but lead the point to PG. And now the trick is that choose a weak equivalence. Again, essentially by design. It is a weak equivalence by the proposition we proved before. And now we can take a canonical pointing here of both ends. We pick the identity of G in both. And we consider the associated fibers of these maps. What we get here, well, we get the maps from H to G, such that if we consider only the image of the unit of H, it goes to the unit of G. Of course, everything up to homotopy, but the point is that what we get are the mapping space in orb pointed between BH and BG. Where H and G are pointed canonical identities. And if we take this fiber here, if you play around with the colimit, which defines the geometric realization of these here, what you have is simply a map of groups between H and G. And hence also the induced map here needs to be an equivalence. And the induced map here is the induced map on mapping spaces by Twisfunker, shown in the claim. Now let me very quickly, to conclude all this, state another result that makes gives some sense to this theory. Is that why did we construct this category orb, and why does the notation suspiciously look like notation for the orbit category of G that we talked about at the very beginning? Well, the point is that we have a couple of positions that come in hand. Well, the first is that we need to introduce something for this. No. Okay. So as we said, we have the we said that if we have a G space, we can turn it into a topological groupoid. But the point is that its inclusion, or rather, its functor here is not fully faithful in general. How can we correct this? Well, we can notice that now the slice comes. That's where the slice is supposed to go. You have a terminal object here, point with a trivial G action. Therefore, in particular, this functor here will factor as first through category of topological, the slice category of topological groupoids over the image of the point. It is the image of the point with the trivial G action. It's the classifying groupoid, topological groupoid of G. Now, the statement is that this induced functor here is fully faithful. Also, this is nothing conceptual. Just write down the mapping spaces and you do things by hand, as we did before. And just give a second to collect my thoughts. Yes, we can refine the statement a bit. And that is that we said that if you remember at the very beginning, when we defined the orbit category of a group G, we said that it is a certain full subcategory here, namely the one spanned by quotients of the form G mod H. And therefore, it makes sense to see what happens at this full subcategory under this functor. And what you find out is that there is a commutative diagram of fully faithful functors where we have this orbit category of G. Oh, sorry, not all of them are going to be fully faithful. And then, or at least that's not the point. No, sorry, my bad. This is exactly part of the statement. So we said OG is a subcategory of G spaces. Here we can embed into topological groupoids over VG. And now here we have we can restrict not to all topological groupoids, but to those of the form of this form. So classifying spaces for classifying topological groupoids for some group, that is objects in the orbit category. Still over PG. And now the point of the proposition is that this square is really closable. So this functor here really induces functor from the orbit category of G to this global category of orbits over BG. And the way this functor is going to be defined is exactly the same, but let me spell it out. So if we have G mod H here, this goes to is BH into BG. And this is actually the functor that we care about, because this gives us a way to now to relate this theory with the classical one, where the base group is fixed. Namely, yeah, well, first of all, at the end of the talk, maybe it would be time to actually mention again the title. This we remember at the beginning that we had this orbit category over a fixed group, and we noticed we saw via the Elmendorf's theorem that presheaves, or this orbit category associated to G, are really the same thing as G spaces. And we got a hint via this proposition here that the orbit category of a group G lives inside at least a certain slice of this global orbit category. You see, this is a couple of messages. Guess that they are not questions.
No,
Yes, okay.
no, there are no questions.
Okay.
It's just that we are a bit out of time, so that's that.
Yeah, I know. Sorry for that.
Sure.
This is the last statement. That is, so we said we have this. We saw that this orbit category associated to G lives more or less inside this global orbit category. So why don't we try and copy things? And we say that orbit space is a presheaf over this global orbit category. And finally, the last statement is that if we have again a compactly group And we have again a fully faithful functor. Which is given as follows. Go from G spaces via Elmendorf's theorem to two sheaves for the orbit category of G. Now we left can extend the inclusion that we had before of orbit G inside the global orbit category over G. And since that was a fully facial functor, its left can extension is going to be as well. And finally, can pull this thing out as a slice. I can go to Orbispaces over BG. And so what this tells us is that if we you can view G spaces as certain kinds of Orbispaces leaving over the object associated to the classifying groupoid of G. And you can also characterize the image of this as those Orbispaces over BG that are representable, but since we are out of time, I will skip this. And apologizing for being very, very late. I think I can end the talk here and available for any question.
Yes, let's thank the speaker. So yeah, are there any questions?
Let me maybe mention a thing that did not appear in the result, so maybe should have been, that is stacks.
Yep.
Yeah, the point is that for all of these, actually, as you see, you don't need stacks. It just depends on the definition that you take of this global orbit category. What you can do, however, is that again you can turn so a stack is simply a sheaf of groupoids on the category of topological spaces, transferred to the canonical topology that you have in there, or if you prefer, take the étale one, it doesn't matter. And given a topological groupoid, you can turn it into a stack, namely the stack of principal G bundles. Right. In particular, you if you define mapping spaces the correct way for stacks as well, you can define orb not as a full subcategory of topological groupoids, but rather as a full subcategory of stacks.
Stacks, yeah. Right, right.
With the mapping spaces defined there. However,
I think that's what Ketna do, right?
Yes, exactly. That's what I do. But the problem is that, I mean, if you do that, you also have then a nice comparison between the Orbispace that you get in the that you get out of this function here, and the stack associated to the topological groupoid associated to G space, and you can relate the two. But if you just want to describe the category orb, they don't need to appear. So that's why I skipped them.
Sure. Yeah, if there are no more questions, let's thank our speaker again. It was a pleasure. That was great.
Yeah.
So
Thanks
maybe
for
I'll stop the
accepting me.
recording and